Hello and welcome to Lecture 8 on the method of partial fractions part 2. So just like our last video, I have the table set up right here for how you do your partial fraction decomposition. So I'm going to be using this for the rest of this lecture. And over here I have one more important rule that I want you to remember from Calculus 1. And this becomes more applicable now that we're going to be talking about these two cases right here of partial fraction decomposition. So the integral of 1 over x squared plus a squared, a is a constant, dx is going to be equal to 1 over a times arctangent of x over a plus c. So we need this important rule because some of these cases will result in an integral that looks just like this. And remember, this is the same thing as saying tangent inverse of x over a. So you may see either one of those notations, and those are equivalent. All right, let's continue our study of partial fraction decomposition with this example. So my first question for you is this a proper fraction? You should probably always check that before you do a bunch of work and then realize you weren't supposed to do that yet. The degree of the numerator is 2. The degree of the denominator is 3. So yes, this is a proper fraction. So the degree of the numerator is strictly less than the degree of the denominator. So I'm going to go ahead and factor the denominator if I can. And there is one thing that I can do here. So what I can do is I can factor out that x, and I get x times x squared plus 4. And then this is irreducible. This right here cannot be factored over the real numbers. There's no such thing as the sum of squares. You probably heard that in Algebra 2 class before. There is a difference of squares, but there's not a sum of 2 squares over the real numbers. So I have two factors here. This one is a linear non-repeating. So this is case 1. This one is an irreducible, and it's also not repeating because it's to the power of 1. So we're looking at case 1 and case 3. So what I would like to do is I would like to break this up. Let's do some scratch work over here. So 2x squared minus x plus 4 over x times x squared plus 4 is going to have a general decomposition of a over x, takes care of my linear factor. And then this irreducible quadratic is bx plus c over x squared plus 4. Now I'm going to use a combination of methods that I've talked about in the previous video. You can use cover-up method for linear factors, the highest power of linear factors. So for the cover-up method, remember you can only do this on the linear factors, and they have to be the highest power. I should be able to find a. So x equals 0 is what makes the denominator here 0. And if I cover up the x over here in the main fraction and plug in 0 everywhere else, I get 4 in the numerator. And if I plug in 0, I get 4 in the denominator. Remember, we're ignoring the factor of x to make this defined. So a is 1. You cannot use cover-up method to take care of a nonlinear factor. So now what I'm going to go ahead and do is I'm going to say, OK, well, a is equal to 1. And I'm going to multiply both sides by the least common denominator. So that's going to be x squared plus 4. Let's take care of that down here. So denominator cancels on the left side. I get 2x squared minus x plus 4 equals. Here I'm going to get the x's cancel, and I get a x squared plus 4. And then I'm going to get plus bx plus c. And this is times x, because the x squared plus 4 is cancel. So now from here, I'm going to erase a, because a is 1. Right? A is 1. So please just allow me to do that. And now I'm going to examine this and look at what b and c are supposed to be. So there's 2 x squareds over here. Let's see the x squareds I've got going on over here. Here I have 1x squared plus 4. If you distribute this, here I have a bx squared. And then I have a cx here. So if I collect all my x squareds over here, this tells me that 2 is supposed to be 1 plus b. So immediately I know b is 1. OK, can I do anything like that to get c? I can. So the coefficient in front of just the x term is -1. So -1x's are on the left side. Where are my x terms over here? Well, that's not an x term. That's a constant. This is not going to be an x term, but this last one is. This is the only one on the right side. It's cx. So that tells you immediately, if you match these up, c has got to be -1. So now I've got a, b, and c. So I can go ahead and write what my integral is supposed to be. So this integral I had before, the 2x squared minus x plus 4 over x squared plus 4. This is equal to the integral of a over x, which is going to be 1 over x, plus the integral of b is 1, and c is -1, over, and then here I have x squared plus 4 dx. So now the problem reduces to, can I integrate both of these things separately? And yes, I can. So what I'm going to do for this is the first one is one of the rules we learned in the last video. We didn't learn it, but it was a review. I have 1 over x is ln of x, absolute value of x. For this, I'm going to take this factor, and I'm going to break this apart. So this is the same thing as the integral of x over x squared plus 4 minus, and then 1 over x squared plus 4 dx. And then I need to do each of these integrals separately. So the first one, I can use a u sub. I could say u is equal to x squared plus 4. And this would tell me that du is equal to 2x dx. So let's go over here and finish the problem. So I have ln of absolute value of x plus the integral. Here, the denominator is u. And then here I have 1/2 du is x dx. So I get 1/2 du is equal to the dx here, the x dx, which is right there. And then minus, this is the rule that I just talked about. So here I have 1 over x squared plus 4. This time my a is 2. So this integral right here is going to be 1 over 2 tangent inverse of x over 2 plus c. And then all that's left for me to do is integrate this middle piece right here. So I get ln of x plus 1/2 ln of absolute value of u minus 1/2 tangent inverse x over 2 plus c. And then we know that the u that I chose was x squared plus 4. And I'm just going to write the rest of this. OK, and then that's it. So with this problem, I introduced an example where I used this third case right here, where I had a quadratic irreducible. And it involved using this new rule. So in just a moment, we're going to start another example. OK, so welcome back. I have our next example on the board. The question with this one is, what happens if we have a single irreducible quadratic as our denominator? So now partial fractions isn't going to help because I only have one factor down here. This would be equal to some integral ax plus b over x squared plus 4x plus 13. But if you compare the two, we automatically know what that is. A is supposed to be 1 and b is 0. We don't get anywhere by using partial fraction decomposition. So we need another way out of this. Well, we've already learned the method to handle this, and it's called completing the square. We're going to complete the square. So we're going to complete this square, x squared plus 4x plus 13. Our a is 1, so we don't have to factor that out. We're going to take half the b term and square it, which is half of 4 is 2 squared is 4. And then to keep things equal, it would be 4 plus 9. That's what we're going to split 13 into. So then for this, I get x plus 2 squared. That's my completing the square. And this is plus 3 squared. So now I'm going to go ahead and fill this in. So this integral right here is the integral from 0 to 1, x over x plus 2 squared plus, and I'm kind of just going to call that 9 dx. Here I'm going to make a u substitution now. So I'm going to let u equal x plus 2. And this tells us that du should be dx. And if you were to rearrange this a little more, you could say that x is equal to u minus 2. All right, let's fill that in here. So I'm going to switch this into u. If you plug in 0 for my lower bound into here, the new lower bound for u is 2. And if you plug in 1 in for x, the new upper bound is 3. X is the same thing as u minus 2. And then here I have u squared plus 9. And dx is du, so I just replace this with du. And then a similar idea to the last problem, I'm going to split this up. So I'm going to say this is u over u squared plus 9 minus 2, just factor that 2 out. And then this is going to be 1 over u squared plus 9 du. And now I have two separate integrals to work with here. Let's move up here. So this right here, this u over this is some form of ln, because here I have the difference in these powers is off by 1. The denominator has a power of 1 greater than this. This is degree 2, this is degree 1. So this is ln of the denominator. However, if you took the derivative of this, you would get a factor of 2 out front. We don't have that here. You would get 2u, so to offset that, you need to put 1/2. So now truly, the derivative of this, you can check it, is going to be this. So if you ever see that the degree of the numerator is 1 less than the denominator, you typically have some kind of ln for the antiderivative. And then in here, I'm going to plug in 3 and 2. All right, how about this one? Well, we did just do this one earlier. So this is variable squared plus constant squared. So 1 over variable squared plus constant squared is going to be 1 over a, which this time 3 is getting squared. And then it's going to be arctangent of u over 3. So this is the antiderivative of this. I'm going to plug in 3 and 2 into this. All right, and then all that's left here is to evaluate. So if you plug in a 3 here, you'd get 1/2 ln of 18 minus ln of 13. And we do minus. I'll bring the 2/3 out. It's all a constant. And then I have arctangent of 3 over 3, which is 1, minus arctangent of 2 over 3. This is the complete answer, but maybe just like a couple things you could do. Remember, if you subtract logs, you actually are doing division. So this is log 18 over 13. And here, we do know what the arctangent of 1 is. What angle is going to give between negative pi over 2 and pi over 2? What angle would be tangent of that angle is 1? It's pi over 4. Tangent of pi over 4 is 1, is what I'm trying to say. We don't have, as far as I know, we don't have a nice answer for this second part, however. So this just looks a little better. OK, so we covered the quadratic irreducible case. I showed you one where you can use partial fractions to break it up. However, if there's only one of them all by themselves, partial fractions is not going to help you. It won't help you get anywhere, like I said. So you'd have to do something similar to this. Maybe use this rule I talked about, or use the ln rule, some combination of the two. All right, in the last part of this video, we're going to be talking about one other application of turning integrals into rational functions and then integrating those. So I'll see you in just a second. All right, welcome to the last part of this video. So sometimes you're going to see integrals where the function inside is not a rational function. For example, if you look at this, I have 1 over x minus root x plus 2. This bottom function here is not a polynomial because roots are not allowed in our definition of polynomial. However, we can often take non-rational functions and change them into rational functions using an appropriate substitution. And then after we've changed them into rational functions, we can go back to our general method of partial fraction decomposition. So let me show you an example here. So here I have this pesky root right here. Sometimes it pays off to substitute out the root. So we're going to say u is x plus 2 to the 1/2 power. And we're going to see what that does to the original integral. So then du would be equal to 1/2, and it would be x plus 2 to the negative 1/2 power, based on the chain rule. You bring the power down, subtract 1 from the power, and the derivative of the inside is just 1. Now this right here is equal to 1 over 2, and then x plus 2 to the 1/2, because I'm bringing that negative power to the denominator. However, that's equal to 1 over 2, and then what did I call x plus 2 to the 1/2? That's u. OK. Let's do one more thing. Here I have x, and I'm going to substitute this out. So let's solve this for x. So first I'm going to square both sides for the first equation. So if you do u squared, you square this, that cancels the 1/2 power, I get x plus 2. And then this just tells me that x is equal to u squared minus 2. All right, I'm satisfied with this. What I'm going to do now, first let me write dx here and dx here. OK, so I'm pretty good with all the stuff I did here. Let's start trying to substitute this, put this in terms of u. So this x right here, I said that that's equal to u squared minus 2. And then this square root of x plus 2, I've called that u. Now up here, I just have to figure out what dx is. So if you solve this right here, here's the left side, and here's the right side. This is a giant equals right here. If you multiply the 2u to the far left side, you get 2u du is dx. So I hope you see that. I just took the far left and the far right one. So instead of dx, I'm going to put 2u du. OK. Let's rewrite this a little bit. So this is the integral of 2u over u squared minus u minus 2. So now that I've rearranged this, I'm going to go ahead and factor the denominator. So this is going to be u minus 2, u plus 1. That's how that factors. It's good that we can do that now that we have this rational function. We basically default back to doing our method of partial fraction decomp. So I need to figure out what this fraction is equal to if I split it up into pieces. And one of the pieces is a over this linear factor plus b over this linear factor. And thankfully, they're both linear, and both of these are the highest power of that factor. I can use the cover-up method for all of it, which is very nice. It's nice when you can just use the cover-up method. So 2 right here would make this term undefined. So cover up the factor over here that goes undefined. 2 would be 4 up here, and then 2 would be 4/3. So a is supposed to be 4/3. And then for b, -1 is what makes this undefined. So you're going to plug in -1 for u, cover up the factor that goes undefined here, like that makes the fraction undefined. If you do -1, you get -2 over -3, which is going to be positive 2/3. So now I can plug these in immediately. So this integral I was interested in, the 2u over u minus 2u plus 1, this breaks up into a, which is 4/3, 1 over u minus 2, plus this b, which is 2/3, 1 over u plus 1. And integrating each of these separately just involves using the ln rule. So this is 4/3 ln of u minus 2 plus 2/3 ln of u plus 1, and then plus c. I guess that's not actually it, right? Because then what I'd have to do is go back to the original variable. So u was actually this. So I'd have the square root of x plus 2 minus 2. And then this u right here was also the square root of x plus 2 minus 2. Or plus 1. Sorry about that. Plus 1. So I guess I do have to go back to the original variable, technically. But then this right here is my answer. OK, so this one is similar in that we need to pick some sort of thing to substitute. What I notice with this one is that the denominator factors right away. Here you get sine of x. And if you factor that out of both of them, you get sine of x plus 1. So to make this look like a rational function, it might be good to have something like u times u plus 1, if you see what I mean. And also the derivative of sine is right there. So that suggests that I could let u equal sine of x, and then du would be cosine of x dx. And let's go ahead and substitute that into this one. So du is cosine of x dx, and this is going to be u for sine, and then u plus 1 for sine plus 1. So my goal here is to break this up. So let's do that over here. So I have 1 over u times u plus 1. Again, I'm in the case where both of these are linear and both of them are non-repeated. So I just need an a for the u and then a b for the u plus 1, so 1 for each. And again, I can use cover-up method, which is very nice. So I'll use cover-up method. 0 is what makes this fraction undefined. So if u is 0, ignore the u here. If you plug in 0, you get 1 over 1. So a should be 1. And then similarly, if u is -1 here, then I'm going to cover up this factor, 1 over -1, which is going to be b is -1. So this just tells me that if I have that this integral breaks up into a over u, which is 1 over u, and then minus 1 for b, minus, and then 1 over u plus 1. So now that we've decomposed this, I can use my log rules for each of these integrals. So this first one is just ln of u, and then I'm going to get minus ln of u plus 1 plus c. And then this time I will not forget to go back and plug in what u was. So this time u was sine of x. So each of these u's, I'm just going to go back to the original variable and plug in sine of x. And then that's my answer. OK, so some integrals might not look like you can do partial fraction decomposition, but with a clever substitution, you might be able to turn it into something that you can go back to using these rules for. So in this example, we turned it into this rational function, and in this example, we turned it into this rational function. So practice a lot of examples of these. Also go back to your old examples and mix them all together. It's not very helpful to practice just one technique in a vacuum at a time. You want to put yourself in a situation where you're trying to also figure out what technique do I need to start with, because on the exam, we're going to mix them all together. And in the next 2 lectures, I'm going to help you do just that. So be prepared for that. But until then, I will see you. Please send me any questions you have. Have a nice day.